All right, so last Thursday we finished up talking about hydration reactions. We said that you can do Markovnikov hydration by using dilute acid, or you can do the oxymercuration demercuration. Again, just to review, why would we ever want to use the oxymercuration demercuration? It avoids rearrangement reactions, right? They both give you Markovnikov hydration products, though. All right, if we want to do anti-Markovnikov hydration, that's when we use the hydroboration oxidation mechanism, and that gives you anti-Markovnikov alcohols. And we said the reason for that is that the borane will essentially dock with an alkene and get installed off of the less substituted position. Why do you think that boron prefers to bond with the less substituted carbon? Sterics, right? It's a lot easier to dock with the less substituted carbon due to size. All right, and then I said there's a supplemental video on the website where you can watch the overall transformation. I'm not going to expect you to do the whole mechanism just because it takes like 15 plus minutes to draw out the whole mechanism for this reaction. All right, I did want to show you an example of this though, and this actually goes back to the pod. All right, and for this example, we're going to use the alkene from the pod. And we're going to treat this with BH3THF in step 1. And then we're going to oxidize it in step 2 using sodium hydroxide and hydrogen peroxide. And like we saw, it's going to prefer to hydrate the less substituted anti-Markovnikov position. So your new alcohol, when it comes in, will come off of that upper position. And you're also going to install a hydrogen off the other side. The methyl group that was on there will be like that. And you'll also get the enantiomer as well. The key thing with this, though, if you look at it, is the alcohol that's added across the double bond and the hydrogen are always going to be on the same side. So either they're both going to be dashes or they're both going to be wedges. Does anybody know what this is called? It's not anti-addition anymore. It'd be syn addition. All right, so you always get the syn addition product, and your alcohol is always going to be installed in that anti-Markovnikov position, meaning it's going to come off that less substituted side. All right, I'll show you a really simple trick, too, that students use as just a memory aid. And that is, if you see peroxides, you should think of anti-Markovnikov addition. Does anybody remember the other reaction where we used peroxides? It was when we used HBr and peroxides, right? That also gave us the anti-Markovnikov addition, but in that situation, we got anti-Markovnikov addition of a halogen. So those are the two main reactions that will give us anti-Markovnikov addition. Make sense? All right. Now we got to jump into one that's kind of a crossover reaction, where we're going to install both an alcohol and a halogen. All right, and this is called a halohydrin reaction. All right, and in a halohydrin reaction, what you have is you have elemental bromine, so Br2, and you have this mixed in with water. It's kind of a weird reaction, but elemental bromine's somewhat soluble in water, so you can try to mix them up as best you can. Most of the bromine will just kind of sink to the bottom, and then you have this kind of pinkish aqueous layer on top of elemental bromine mixed with water. All right, in the first reaction, we'll see something we've seen before where this pi bond will attack the bromine will attack back in and will kick off our bromide in order to give us a three-membered ring. Does anybody remember what the three-membered ring is called? It's a bromonium ion. All right, we still have bromide floating around and we still have water floating around. The key thing with this reaction though is you have a huge excess of water. That means you've got a lot more water molecules floating around than you do bromide ions, which means in this next step, water is more likely to attack one of these carbons than the bromide ion. So let's make a note of that. Water outcompetes Br minus as a nucleophile. All right, so after this reaction occurs, you'll have a bromine that is now on the opposite face of where the water added in. So it's anti. However, in this situation, it doesn't really matter because we just have methyl groups floating around. And like I said, this is done with a huge excess of water. So what do you think our last step is going to be? Yeah, deprotonation. So our water is going to grab this proton, pop this off. Look at our alcohol, anti to our bromine. And just like we saw with the reaction with elemental bromine, we get anti-addition. This time, though, instead of getting two bromines, we get one bromine and one alcohol. The other cool thing with this reaction is it also works with chlorine. Does anybody know why the reaction with chlorine is a lot less common than the reaction with bromine, though? Yeah, chlorine's a lot less selective, and it's a poisonous gas. So that would be one of the more practical reasons. Yeah?
You said that water outcompetes the bromine line just out of your concentration?
Yes, just simply based on concentration. You have such a huge excess of water, it's just going to outcompete bromide. Yep, great question. All right, so this reaction's kind of neat. The other thing that you can do with this reaction, and I want to make a note of this, is that other alcohols can be used. So in this example, we use water, but you could use methanol, ethanol, any other sort of alcohol as a nucleophile for that ring opening reaction in the second step. So really, this is a pretty useful reaction for creating two different functional groups at the same time. Yeah?
So is this one of the 68 reactions that we need to know?
This is one of the 68 reactions we need to know. Like I said, though, a lot of these are just variations on one another. So one alcohol versus another alcohol, they're remarkably similar. Yeah?
Does this one always form anti-addition?
Yes, it'll always do anti-addition because we're going through the three-membered bromonium ion. So you'll never get syn-addition because that top face attack's just two-hindered. Yep. All right, so now we need to talk a bit more about regiochemistry. And I will say that a note that's in the box right above might help you with the pod. Hint, hint. All right, so now let's jump into the regiochemistry of the halohydrin reaction. Let's say we've got an alkene where one carbon is more substituted than the other carbon. So right, that carbon on the left has two methyl groups, the carbon on the right's just got two hydrogens. In the first step, everything's going to be exactly the same. We're going to react this with elemental bromine and water. We know that the double bond can attack the bromine can attack back in, and we'll kick off bromine as a leaving group. We go through this bromonium ion. We have water floating around. We know that water in this case is going to outcompete bromide as our nucleophile. But then the question is, which carbon is going to be attacked? So let's consider two possible outcomes. All right, one outcome I'll show with a red arrow. We could attack this carbon right here, and we could slingshot this open. And let's consider the transition state for this. So in this transition state, we're breaking the bond between that carbon and the bromine, right? And we're forming a bond to this water molecule. In this transition state, bromine's losing its positive charge, so it'll be partial positive. Oxygen's gaining a positive charge, so it will also be partial positive. So that's one option. So this is the red pathway. Let's consider the blue pathway, though, where maybe we attack the other side and we slingshot open the bromine. All right, in this other reaction, the bond between the carbon and the bromine is being broken. The methyl groups are going to kind of flatten out a little bit. And this oxygen is going to have a partial positive. This bromine is going to be partial positive. And there we go. So we've got these two competing transition states. All right. Which transition state do you think is more stable? The left or the right? Think about the carbon, right? If we think about the bromine in each of these, the bromine's partial positive versus partial positive. If we think about the oxygen, it's partial positive versus partial positive. Really, the only difference I'm seeing between these is the carbon that's being attacked. Which carbon's going to be happier going through the transition state? Probably the left-hand side one, right? So we'd say this is the more stable transition state. Come on. Oh, my goodness. Well, it looks like this may be going back to Microsoft. Sorry. So this is the more stable transition state. That carbon that's highlighted in yellow is a tertiary carbon. It's a lot happier going through a polarized transition state than a methyl carbon, kind of shown on the right-hand side. So this was much more likely to occur. This is going to be our less stable transition state. However, we will see examples later on in the year where you could make an argument that sterics plays a role too, right? If we're thinking about sterics, you could argue the one on the right's maybe more favorable, but in this example, experimentally, we know that this transition state on the left is far more likely to occur. All right, so now if we think about this reaction, we can consider our product that we're going to get out. And we're going to lose this proton off of water. And our alcohol is going to be installed off of the more substituted carbon. So let's make a note of this. Does that make sense? So essentially the alcohol is getting installed at that Markovnikov site. The bromine is going to be off your anti-Markovnikov site. Yeah?
When you mentioned up in the transition states about sterics, though, so it's not impossible, say if we did it under incredibly high temperature, could we favor the less stable transition state?
That's a good question. So the question was about these two transition states. Oftentimes what chemists do is they have to consider both electronics, which is what we were arguing here. So how stable is that carbon, or sterics? And it's not always clear which will win, sterics or electronics. In this example, we know that electronics wins out because of the products that we observe. That's really our only rationale for that. It's kind of counterintuitive, but oftentimes the way I was taught was that we learn that reaction mechanisms are plausible, but we can never prove them right. However, we can prove reaction mechanisms wrong, meaning we don't get the anticipated products. So it gets into this weird abstract idea of what's going on in the reaction. All right, so I know that is a little bit weird. All right, so let's try another one. Let's consider this reaction, where we have elemental bromine and we've got water, but now we've got a different sort of alkene. All right? In the first step, like we saw before, this pi bond is going to reach out, grab a bromine. Bromine will attack back in. We'll kick off bromide. All right? We could have the top face attack where that bromine essentially acts as a bridge over the top, right? And the carbon on the left has a methyl group kind of pointed out. And then we also have an ethyl group off of that carbon, right? And then the back carbon, we still have the methyl group, but it's going to be on the opposite face of the methyl group on the left, right? Just for clarity's sake, I'm even going to show this hydrogen. Does that make sense so far? So we've got this hydrogen right here that's on the same face as the methyl group. That needs to be on the same face during our intermediate. All right, alternatively, we could show the bromine acting as a bridge underneath. And it could look like this. What's the relationship between these? Are they identical? No, they're enantiomers of one another, right? They're non-superimposable mirror images of one another. Okay, so now we've got these two enantiomers. We have water floating around that could react with either of these enantiomers. And like we said, water prefers to attack the more substituted carbon. So in this one, it could attack this carbon right here, kick up our bromine. That happens, we still have this hydrogen and we still have that methyl group, but now our water is going to be anti.
Quick dumb question, why is that more substituted carbon?
Yeah, good question. Just let me finish this last part here. If we think about this carbon on the left, right, that's bonded to 3 other carbons, versus this carbon over here, it's only bonded to 2 carbons, right? So it's more substituted because it's bonded to more carbons. Good question, though. All right, so now we've done this anti-addition attack. Let's do the same thing for the other one. It's still going to prefer to attack this carbon over here. It's still going to slingshot open that bromine. Now we've got water anti. So now we still have these anti-addition products. Make sense? What do you think the last step's going to be? Deprotonation, right? So we could show this as minus H plus, and this one as minus H plus. If we do that, we're just going to rip off one of these protons off of water, or sorry, off of our alcohol. And for this one on the right, we're still going to have anti-addition. So if we look at these two products, like we said before, we're going to get a mixture of enantiomers. Whoops. Do you think we're going to get one over the other, or do you think they're both going to be equally likely? Equal, right? So in this example, we'd get a 50-50 mixture of enantiomers. This would be a racemic mixture, and it wouldn't be optically active anymore, right? In each situation, though, if you notice, our alcohol came off the less substituted carbon, and our bromine came off the least substituted carbon. So we can't predict our products, but just like before, we need to watch out for stereoisomers. Yeah?
When we're doing this on the physics for the reactions, do you want us to draw both?
That's a good question. So the question was, do you have to draw the formation of both products? Not necessarily. What you can do as shorthand is just write plus En, and I'll understand that you're referring to the enantiomer doing the same thing. Yeah, good question. All right. So now we're kind of hodgepodging the alcohols and the halogens, installing both at the same time. Now what we need to do is figure out how to install two alcohols at the same time. So we're going to start out talking about anti-dihydroxylation. And I'll show you what I mean by this. Let's say we have an alkene, and we want to install alcohols off of both sides of the alkenes. That means one alcohol would be a wedge, the other one would be a dash. However, we don't have really good control over this, so we could end up with an enantiomer as well. We have a set of reagents that are pretty commonly used, and I apologize beforehand, it's more alphabet soup. So it's MCPBA, followed by acid and water. So now the question is, what is MCPBA? Well, naturally, it's metachloroperoxybenzoic acid. That'll win Scrabble for you. So MCPBA. Most people just refer to it as MCPBA. It rolls off the tongue a little bit better than metachloroperoxybenzoic acid. All right, so let's take a look at what this looks like. If we think about benzoic acid, it's a carboxylic acid coming off of benzene. Peroxybenzoic acid means that it's kind of in between a peroxide and a carboxylic acid. So this is peroxybenzoic acid. And then we need to add a chlorine off of the meta position, which essentially just means position number 3. And this is MCPBA. Essentially, what chemists were doing was they were trying to figure out which peroxy acids work the best for these. MCPBA works best under most circumstances, so it's kind of our go-to peroxy acid. Yeah?
Are we going to need to be able to like draw out what MCPA is? Is it something that's going to be like on a test or something we're really going to?
So the question is, do I want you to memorize the structure? Not exactly. It's good to know. For example, on the ACS exam, they'll actually give you a key with the alphabet soup and the corresponding structure. So they'll say like MCPBA, here's the structure. They won't tell you what it does though. I want you to know what it does. So in this example, we saw MCPBA in the first step, followed by acid and water will always give you anti-addition of alcohols. So it'll give you anti-addition of 2 different alcohols. All right, so now we need to jump into the mechanism a bit more.
Jeff?
Yeah.
So just theoretically, if we use this in a reaction like HBr, since it's peroxy, would it do anti-Markovnikov?
Well, in this case, we're adding 2 different things. We can't really call it anti-Markovnikov or Markovnikov because we're adding 2 identical alcohols, right?
Yeah.
So I wouldn't really refer to this as Markovnikov or anti-Markovnikov. Yeah. All right, sometimes too, I will warn you that this group right here can vary from time to time. So I think on saplings, sometimes they show that as a CH3 group. It'll still do the same reaction. It's MCPBA is the more common one though. All right, so let's take a look at the mechanism. All right, the mechanism is kind of weird, so bear with me. I'm not going to show the whole benzoic acid part, so meaning this whole R group up here. I'm just going to abbreviate that as R. Makes it a little bit easier for us. So peroxybenzoic acid likes to hydrogen bond to itself. So if we think about it, right? The lone pair on this oxygen can really loosely coordinate with that hydrogen coming off right there. Make sense? So it's an intramolecular H bond. All right, so if we think about this, that hydrogen's being tugged on by the carbonyl oxygen, and this oxygen down here is pulling electron density. That means that this poor little guy right here really doesn't have very much electron density anymore. It's highly reactive because of that. So in this first step, what will occur is this pi bond will attack this oxygen because it's so electron poor. And then this oxygen at the same time will attack back in to the pi bond, kind of like we saw with the bromine reaction. In the next step, we need to break bonds to that oxygen. It can't have 4 different bonds to oxygen. That's just simply not allowed. So we're going to break the sigma bond, dump it over, but then at that point, this carbon right here violates the octet rule, but we can fix that. So what we're going to do is we're going to take one of these pi bonds, and we're going to have this pi bond basically form a new sigma bond to that proton, all in one step. I know, it's a lot to look at right here.
All in one step?
Yeah, pretty much. And then this is going to hop over like that. So I know everyone's looking at me like, you've got to be kidding me. This is way too much right now. I'm just showing you this mechanism. I'm not going to expect you to regurgitate this on an exam. So let's take a look at the transition state, though, because the transition state's kind of interesting to look at. So we're forming this 3-membered ring to oxygen. The bond is being broken to that hydrogen. It's being broken to that oxygen. We're forming a new bond with this hydrogen. We still have this R group. I don't know, I think it's kind of pretty. So it's this big, kind of funky looking transition state. All right, in the next step though, what's going to happen is we're going to be left with a 3-membered ring to oxygen. And then up here, we're going to be left with this oxygen down here having a double bond. And the R group is still hanging out. What new functional group did we make on the right-hand side? Carboxylic acid. This is our byproduct. Really, the thing that we care about the most, though, is this weird-looking 3-membered ring. This is called an epoxide. All right, so epoxides are really important. We're actually going to cover them a fair amount when we get into ethers. So if we think about it, an epoxide is just a fancy ether. However, do you think it's a very happy ether? Why not? The bond angles are way, way, way out of Vesper theory. So these epoxides are highly reactive. They don't want to have that 60-degree bond angle. They'd rather be about 109.5. So they're going to be super duper reactive. All right, so now we've made this mixture of products in our first step. we can do a really simple purification, get rid of that carboxylic acid and isolate our epoxide. If we think about step 2, if we go back up and look at it, it was acid and water. So let's take a look at what would happen if we treat this epoxide with acid. Acid-base chemistry is the fastest reaction. So we can think about protonating the oxygen on our epoxide. All right, this looks even less happy, right? So not only does this now have angle strain, meaning it's way outside of VSEPR alignment, but that oxygen now has a positive charge. This is not a happy camper. So what we need to do next is have water attack in. But just like we saw before with that reaction where we had the bromonium ion with the positive charge, water can attack one of those sides. So in this side, or in this case, it doesn't matter. Each carbon is equally substituted. So it doesn't have a strong preference of one carbon over the other. And it's going to slingshot this open. Let's go back, though, and think about this. If we think about each of these carbons right here, technically they are stereocenters, so there must be some geometry to them. So, for example, we could show this with dashes or wedges. So if you want in your notes, show this with bold lines. Why can't it be both a dash and a wedge? Geometrically, that would be impossible, right? So it's got to be either both dashes or both wedges. In this case, we're lucky because it's a meso compound. All right, so if water attacks in underneath, this is basically a fancy SN2 reaction. So I'll just write SN2. It's going to do that backside attack and slingshot it open. And if water's doing a backside attack, that means it must have attacked in as a dash. And this alcohol would have been, whoa, come on, like that. Or conversely, I'm going to show this down here. We could have had water attack the other carbon, which is right here, slingshot this open. It's still going to be an SN2, but if it did the backside attack on the bottom carbon, that means that the water would have been a dash off of this position. What's the relationship between these? They're just enantiomers, right? What do you think the last step's going to be? Yeah, deprotonation. So we can go ahead and we could say minus H plus. Same thing down here. So in this one, we would have alcohol right there, alcohol right here. For this one, we'd have an alcohol off of each of those. In both situations, they're anti-addition products, but we will still get a 50-50 mix of enantiomers. Does that make sense? Like I said, we'll come back and talk about epoxides in a lot more detail. The cool thing with this is this step right here, where water was attacking in, you can use a ton of different nucleophiles to ring open epoxides and get a wide variety of different potential functional groups. Do you have a question?
Why would, so the second part of this reaction,
Yeah.
why would that second step happen at all if it was so unhappy in that form where we have the positive on the oxygen and we have those horrible bond angles? Why would it ever grab on?
Yeah, that's a good question. So the question is, why does the protonation of the epoxide take place? If we think about acid-base chemistry way back to first term, we talked about them being equilibrium reactions, right? So this could occur. Maybe it only occurs at 0.1%. Even at that 0.1%, that intermediate's so reactive, it'll immediately react with water and drive the reaction forward. So we can think about it as being unfavorable, but still it'll push the reaction forward. Does that make more sense? Okay. All right, we've got a couple more dihydroxylation reactions. If we think about these ones, these were both anti-addition. However, we can do syn addition as well. I've got good news and bad news. The good news is you don't need to know the mechanism. The bad news is there's two different ways to do this. And then we'll call it good for the day. So the first one uses osmium tetroxide, so OSO4, followed by sodium bisulfite, NaHSO3, and water. And that will install two different alcohols in a syn orientation. For this particular example, do I need to worry about stereoisomers? Why not? It's a meso compound. However, if we have other functional groups coming off, meaning there's no plane of symmetry, then we would have to worry about getting a mixture of stereoisomers. This is kind of a crazy reaction. I don't think they talk about this in your textbook very often, but this reagent, osmium tetroxide, I'm not scared of a lot of reagents, but I'm scared of this one. The way our vision works is inside of our eyes, we have rods and cones, right? How many of you have heard about that in biology? So inside of those rods and cones, you have a bunch of photoreceptors that contain alkenes. And those alkenes are sensitive to various wavelengths of light, right? And that's how we see. The problem with osmium tetroxide is if you get those vapors in your eyes, it will react with the alkenes in your eyeballs and make you go blind. Most chemists, because of that, prefer to avoid using osmium tetroxide at all. However, sometimes you can't avoid it, so then they need to use it catalytically, and they'll use a different set of reagents to avoid using it at a very high concentration. So it is kind of a scary reagent. I like sharing that with people. All right. Second one is a bit more common. However, it has its own unique set of problems. Oh my goodness. This is KMnO4. This is potassium permanganate. Ugh. I'm going to have to take my laptop in. And you have to do this reaction cold. Potassium permanganate, KMnO4, is a really, really, really strong oxidizer. If you run this hot enough, it'll actually break apart carbon-carbon double bonds and form two carboxylic acids. So we don't want to do that. We just want to stop at the alcohol. And this will give you the exact same diol. The other problem with potassium permanganate is because it's such a strong oxidant, it'll do other chemistry that we haven't even learned yet. So sometimes we can't use this, sometimes we can. However, we've got two options for doing this syn dihydroxylation. So I'll make a note here. The note is you don't need to know the mechanism. All right, I think that's where we're going to stop today. We do have like 5 minutes left, though, so if you want, you can start working on your problem of the day. I always recommend trying to get it started earlier rather than later so you have enough time to think about it and ask questions if any of them come up.